Okay, the first method is called the Jacobi iterative method. And as usual, I'll sort of give you the intuition and then we'll solve a problem. So here's the intuition. Let's say that we want to solve a system of two equations in two unknowns. So what Jacobi method does is it tries to solve for x1 first in terms of x2. So b1 minus a12 x2 divided by a11. And then we'll write another equation for x2 from 2. So x2 equals b2 minus a21 x1 divided by a22. So essentially, we're using sort of the diagonal elements, right? So we're using this one and this one to solve for x1, x2. Clearly, you cannot solve for x1, x2 this way because x2 in the first equation, x2 is also unknown, right? And then second equation, x1 is unknown. So how do you proceed? Well, what this method does is essentially, so all iterative methods starts with a guess with some space here. So start with the initial guess. Okay, let's say the guess is x1, x2, and the 0 superscript means that's for iteration 1, iteration 0. So then for iteration 1, so now we are trying to improve on the value from the guess. So how about we try to use this guessed values to improve x1, x2. So what we'll do here is we'll compute a new solution for x1. So iteration 1 is b1 minus a21. In here, in the first equation, we'll substitute the value we have for the initial guess for x2. And we do the same thing for x2. It's b2 minus a21 x10 a22. Okay, so we're using the initial guess to improve on the solution for x1, x2 in this fashion. I hope that from the way I've written it down, it's obvious what's happening here. Now we can do the same thing for the next iteration. So the same thing happens for the next iteration, except that now we have a new solution x1, 1, x2, 1, which is an improvement. So let's use that. So iteration 2, this is the new solution. We'll use solution for iteration 1. Keep doing this till convergence. Okay, so what convergence means here is, remember all the methods have 3 elements to it. One is the initial guess, which we have x10, x20. The search is basically this method, iteration 1, what I've showed you there. And then the convergence. So the convergence is, what you can do is try to see if x1 values are beginning to remain the same. So if you get a solution for x1 iteration n and it does not change between two iterations, then you can say that it's converging, and so you will not, you'll quit. So keep doing this till convergence, and convergence could be one, it could be x1 iteration I minus x1 iteration I minus 1, so that's the previous iteration, is less than some epsilon, so less than some epsilon. Or you could also, well, you have to check this for both, right? So we'll do and x2 iteration I minus x2 iteration I minus 1. So both of these conditions need to be true, because if one of them is violated, that means the one of them has not converged, right? So another way you could do this, so you could do this for if there are like n variables, you could do it for n variables, or you could just do it this way. You could just create one number which encompasses all the variables, something like this. So on is less than epsilon. So this epsilon is a user defined tolerance. Example, if you want very accurate, you could maybe go 1e negative 6, or you could have 1e negative 3. Just depends on what you want. You want the solution to be very accurate, you want to go 1e negative 6. If you don't want it so accurate, you can go 1e negative 3. It turns out that the higher the tolerance you demand, the more number of iterations it will take, and maybe you don't have the time to wait that much iterations. This will happen if you're trying to do this real time, which happens in many applications. You're doing these computations online, in which case you want to stop early. Or if you have all the time, it's an offline experiment, you're free to do it for more iterations, which means you can put a more stringent tolerance. Okay, so let's take this approach in with the same set of equations we discussed earlier, because we know the solution to that. Okay, so here is the problem. Solve for x1, x2, x3 using Jacobi method. So 2x1 plus x2 plus x3 equals 7. x1 minus 3x2 plus x3 equals minus 2. 2x1 plus 2x2 minus x3 equals 3. Use initial guess x1 0 equals x2 0 equals x3 0 equals 0. Solve up to 3 iterations. Okay, and the reason why 3 iterations is that it actually takes, I written the code, it takes about 500 plus iterations to get it to converge. So we don't want to solve it by hand for 500 iterations. So let's just do 3 iterations. And when we do these calculations using code, we'll compare our answers to the first 3 iterations. Okay, so let's proceed. So the solution, what I'll do is I'll get ready to use the Jacobi method, which means I'll try to solve for x1, x2, x3 using those 3 equations. So let me write an equation for x1. It's 7 minus x2 minus x3 divided by 2. One, two, three. From 1, another one here from 2, and from 3. x2 is -2 minus x1 plus 3x2 plus 3x2 minus -2 minus x1 is right, and minus x3. The x2 remains there, and then divided by -3, and then x3 equals 3 minus 2x1 minus 2x2. So let's start with iteration 1. So here, what we do is we sub in the value for what we have for the initial guess on the right side of these equations. So I'll do that for the first one. So x1, x2 0 is 0, x3 0 is 0, divided by 2. x2 equals -2 minus 0 divided by -3. x3 is 3 minus 2 times 0 minus 2 times 0 divided, well, this is 1. Okay, and remember that we know the solutions to this. It's, yeah, question. Yes, you've been here, right? Yeah, yeah, my bad. So I need to move this -1 down. You're right. Thanks. Hey, thanks for correcting me. This would be divided by -1. Okay, so what's this? It's 7 divided by 2 is 3.5. This is 2 divided by 3, it's 0.6667. And then this is -3. Again, remember the solution is 1, 2, and 3. And right now we're very far away from 1, 2, and 3. The second one looks okay, but the first one is way off, and the third one is way off. Yes, I like, so I'm using this on a new page, so it just makes more sense to just take it there. I'm going to do iteration 2 now. Okay. I'm just going to take a copy of this, and I highly recommend doing that, so that way it's easy to see this. I'm just going to put this on the right-hand side, like so, and this will serve as a reference for us. Okay, and then what we achieved from iteration 1 is the following solution. x11 was, it was 3.5. x21 was 0.6667, and x31 was -3.5. Okay, with this, we can start doing iteration 2. So x1 is 7 minus x2. So x2 is right here, 0.6667 minus x3 minus 3.5 divided by 2. Okay, so this equation was used to get this. x2, let's look at the second equation. It's -2 minus x1. So remember, you need to use these values. 3.5 minus 3.5 divided by minus 3. So this equation along with this one, I think I did a mistake here. Yeah. Okay, my bad here. I incorrectly copied this. This should be 3 minus 3. Yeah, my bad. This should be 3.5 is at minus 3. So this will be wrong. This should be minus 3, and then this would be minus 3. So okay, and finally x3. So we use the third equation, x3. 3 minus 2 times x1. x1 is 3.5 minus 2 times x2 is 0.6667 divided by minus 1. Okay, so it's a bit of number crunching, but you get 4.6667, 0.8333, and 5.3334. Okay, so before we go iteration 3, let's write down what we achieved. We got the solution for iteration 2. That's 4.6667. x2 2 equals 0.8333, and x32 is 5.3334. Okay, we're ready for iteration 3. Okay. Okay, so I would like you to do it yourself now that I showed you how to do it, and I also marked it up for iteration 2. So try to write down the correct formula here. You should find that your solution is 0.4166, 4.000, 8.000. So please do this at home. And it's always a good idea to try to summarize these things in a table, so it's easy to check your answers. I'm going to make some space here. Okay, so this is what I got. I'm just summarizing all these answers in a table. Iteration 1, we found it was 3.5. Iteration 2, this was 4.6667. Iteration 3, it was 0.4167. For x2, those values were 0.6667, 0.8333, this 4.000. X3 was minus 3, 5.3333, 8.000. Okay, let me box this. Okay, clearly we've not converged to a solution, right? You can see it's the solutions are varying widely, 3.5 for x1, then 4.667, 0.4167. It's going back and forth. So what we'll do is we'll write I'll write a computer code which will give me the answer. And then with the computer code, we can actually see how many iterations it takes to converge. Something like this, I'm just going to use ChatGPT because it's just easier to, it's just faster to generate code using that way. And then I can modify it later on to suit my purposes. So let's see if I can. So let's see. So I have, this was the last problem I solved, Gauss-Jordan. So it's the iterative methods. I'll basically do a new chat. I'm just going to rely on this. So I already have the same questions. I can use this. Okay. So open a new chat. Octave code. Check. Method for the following equations. Okay, we're going to get rid of this. And then I just want it to be formatted in a certain way. Write two files, scripts. The first one is the main file that defines these equations. The second is a function called Jacobi iterative that solves using the Jacobi method. Okay, so I put it as a B, okay. Initial guess, okay, use 0, 0, 0, just like us. Iterations, tolerance, Jacobi iterative. Okay, I did not specify a tolerance, but just put something there. And then here's the function. Okay, I'm going to copy this and see what, if it produces the results we expect. So let's save this. Iterative main Jacobi. Okay, and then the other one was a function call. So copy that. Okay, and then okay, so I don't want to go to the same folder again. So here's what we'll do is a trick. Just to run, and it will probably fail. Just say change directory. And the reason I did that is because now when you go here and say save, it automatically goes to the same directory. Save. Okay. Okay. Okay, so here's the thing. It gave me the solution. It's 1.9, 1.7, 2.9. The actual solution is 1, 2, and 3. And the problem it faced is that number of iterations, 100. It basically reached the number of iterations. It actually should have printed that maximum. It doesn't seem to have printed this. Okay, so this needs to be fixed. It's not printing this. Or maybe there's a display problem. I don't know. We have to do the output thing to check. Anyway, so this code, let's see if the code, well, it's clearly reached the maximum iteration, so I should increase the number of iterations. But just looking at the code, you can see what it's doing. It's basically, we have a formula which looks exactly like this, if you remember. This sum one is probably that everything on the right-hand side of B. And it just checks for, you remember the formula I wrote x minus x square, x1 minus x1 I minus x I minus 1 square plus so on. It actually uses what is known as the infinite norm. we just want to use the 2 norm. So I'll put 2 here. Let's go back and give it maybe 1,000 iterations. Okay, so coming to this, when I run this code, I get 1, 2, and 3, which is the right solution, but it actually reaches the iteration limit. And that's probably because there's some digits you don't see. So if you, I think if you do format long, now it actually prints 13 decimal place accuracy. Let's see if okay, so you can see that the solution is 1.00001 1.9999, but this is not accurate to 6 decimal places, and that's why it is saying maximum iterations leave. So what the easy way to fix this is, of course, to increase the iterations, but let's just go up to, I think 3 decimal places is more than enough. So let's just do that. And you can see it gave me the solution 0.999, which is accurate to 3 decimal places, 2.00, 3.00, and took 583 iterations. A lot of iterations, right? So clearly we don't want to do it by hand. Now, what I said, you can use the Octave code to check your solution, okay, and vice versa. If you think your hand calculations are correct, you could use that to inform the code. Maybe the code is wrong. So let's check if we can get it the same answer as we got using hand calculations for the first 3 iterations. So I'm only going to print 3 iterations because printing 583 iterations is not meaningful. So let's go to this code here. And what we'll do here is we'll just try to assess what we need to print. We have this value x new, which is the updated value. So this stores the value for the new, the values at every iteration. So printing that for the first, second, third, where n is 1 to 3 will make sense. So what we'll do here is I'll go here just after exiting. So this is 1 to max iter. And it is not saving. Okay, it's not saving the solution. So I need to print it right away. So what I'll do is if iter, I think iter is that the name used? Yeah, iter. So if the iterations is less than equal to 3, because I only want to print the first 3 iterations, I'll just make it disp x1 equals, let's see. So x1 is x new 1, x2 equals x new 2, x3 equals x new 3. I think I forgot. Yeah, okay. Okay, let's go back. Okay, so here's the problem. You see, x1, it didn't really print anything. So the reason we did not print anything is because this is a string, a character, while this one is a numeric value. So you cannot mix them up. You need to convert this to a string so it all prints. So the way to do it is to write string to, num to str, I think, num to number to string. Okay, and I need to do it for each and every of those values. So let's just copy this. That should be variable 2. And it should be 3. Okay, let's see if this works. Let's go here. Okay, I need to run this again. So here it is, 3.5.667 minus 3, exactly what we got by hand calculation. 4.667, 0.8335, 0.33. I'm checking it. Yeah, it looks right. And then 0.4167 x2 equals 4, x3 equals 8. It actually printed, oh my God, it printed 4 iterations. So I should change this. So I should just change it from, because iteration was not updated. That's why that happened. So let's go back this code. Okay, why is that happening is because iter is updated here. And so what really I have here is iteration 0. So I just need to truncate this at 0, 1, 2. So should work fine now. Okay, so here it is, 3 iterations. There's a solution and everything we wanted. So this is an easy way for you to check your calculations. Okay, now here's the problem with this method, which is you saw it takes 583 iterations to get a solution. That's not very efficient, right? We clearly want to do this much faster. Okay, but I think it's a much easier method to implement than Gauss elimination, where you have to figure out the pivot and subtract out with the right weights and so on. So there's another method which we'll talk next, which drastically improves the solution or the speed of solution by a very small change. So this motivates the next method, which is called Gauss-Seidel method.